So for sections 6.3 and 6.4, we're going to talk about area under the curve, which then leads us to definite integrals. So definite integrals are basically the equivalent of when we took a derivative and we plugged a value into it, like f prime of 5. So evaluating what that derivative's exact value is. That's the sort of comparison to a definite integral. Whereas an indefinite integral, what we were talking about in sections 6.1 and 6.2, was just about finding the actual antiderivative, just like finding a derivative is just about finding an actual equation or function. So to start off with, we need to introduce a question. What is the area underneath this curve? So meaning if I draw my x and y axis and I look at the following curve here, then what is the area underneath it from, say, x equals 1 to x equals 5? So I've already drawn out this red filled in box here. So I'm asking, what is the area underneath this? If we were to actually draw this shape on its own, it would look something like that. Now, if you look at this, it's very difficult to figure out what this exact area is, because although we have 3 straight edges, this fourth edge has a bend to it along the way, and the only type of object that we know how to find the area of, basically, that has a curved edge is a circle, and we don't know if this is the edge of a circle, so that's not very useful to us. So the only thing we can really do right now is just approximate that area by filling it in with a bunch of objects that we know the area of and then adding them all together. So for instance, what if we tried filling it in with rectangles? What would happen? So if we go to this graph and we say, alright, let's go ahead and just start making a rectangle that's a distance of 1 apart on the x-axis. So if I were to start drawing a rectangle up from 1 and then going horizontal until I reach x equals 2, and then starting at x equals 2 until I hit the graph, and going over horizontal until I hit x equals 3, and then again starting at x equals 3, going up until I hit the graph, going horizontal until x equals 4, and finally going up from x equals 4 until I hit the graph, going horizontal until x equals 5, we'd get these 4 rectangles that when you add the area underneath them together, you'd get a pretty accurate idea of what this area is. It is, however, not perfect because although it's difficult to see on your screen, if you had drawn this with me, you would notice a gap on top of each of these rectangles, which you can hopefully see in red here, of area we missed out on. So, what if we try that exact same process again, but this time we start from the right side. So from 5, we go up, hit the graph, go horizontal until x equals 4, and then we start repeating again. Start from the graph, go to x equals 3, start from the graph, go to x equals 2, and then finally from 2, go to x equals 1. And if we add all of this together, you can probably see what the issue is in this case. We've now overestimated the area. We are adding more than there actually is. So what does that tell us? Well, we need to make a really important note here. So the first thing that we should make note of Let me get a piece of paper here. The first thing we should make note of is a fact that says as the number of rectangles increases to infinity, each of those methods will yield the same value. So that's really important. Think about that. If the value that's overestimating it is getting closer and closer from the top, and the value that's underestimating it is getting closer and closer from the bottom to the curve that we're dealing with, then they're going to meet right in the middle at the curve itself, which means if we put an infinite number of rectangles, we will get the total area under the curve without making any errors. In comes the definition for the definite integral. The definite integral is the limit of the sums of these rectangles as the number of rectangles approaches infinity on an interval a to b. So remember, our interval was 1 to 5 in those problems. So if you put an infinite number of rectangles between some interval like 1 to 5 and you add all of them up, you get the definite integral, which is written the integral from a to b of f of x dx. So notice it's the exact same format as an indefinite integral. The only thing that's changed is we put an a and a b here. So we need to make some more rules that apply to these definite integrals. First of all, we make note that all previous integral rules that we've mentioned in this course still apply to definite integrals. You can pull a constant that's being multiplied to the outside. You can multiply by a constant to the inside and it's reciprocal to the outside, and so on. If you're adding or subtracting, you can break them up into two separate integrals being added or subtracted. You can use U substitution. It all works. From here, the first new rule is that the integral from a to a of f of x dx, meaning if your limits of integration, we call them, are the same, then the integral is automatically equal to 0. Think about why that is. What does it mean for the limits of integration to be the same? It means your rectangles, when you're adding them all up, the width of the rectangle is a minus a, which is 0. So what's the area of a rectangle that has a side of 0? 0. From here, the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx, meaning it is perfectly okay to swap these values as long as when you swap them you multiply by a negative to the outside. This rule also goes backwards. If you have a negative multiplied to the outside of your integral, you can change it to a positive as long as you swap the two limits. And finally, from here, the last small rule that we need to make note of is the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Think about what that's saying. It's saying if we take that interval 1 to 5, so I'll draw this on this separate sheet of paper. If we look at that graph that we started with in the beginning, we had some area underneath it that looked like this. We're saying if you have an interval from 1 to 5, it's perfectly okay to say, well, let's just deal with from 1 to 3 first, and then add that to what we get from 3 to 5. We're breaking up the interval. We still get the same total area when we add the two shapes together. That's why this third step is perfectly okay. Alright, and finally from here we introduce our theorem called the fundamental theorem of calculus. The fundamental theorem of calculus says the integral from a to b of f of x dx is equal to the antiderivative of f of x, remember we use that capital F notation, from a to b. So now that the integral sign is gone, we replace it with this line to show that we've taken the antiderivative, but we still need to keep track of our limits of integration. This line always comes after the antiderivative, so just keep note of that. So it's equal to the antiderivative of f of x from a to b, and that's just equal to f of b minus f of a. The value you get when you plug b into the antiderivative minus the value you get when you plug a into the antiderivative. And now that we have this, we know how to evaluate these definite integrals. So we'll start going through some examples here. The first one, we have the antiderivative from 1 to 4 of 3x squared. Well, in this example, we're taking the antiderivative of 3x squared. This is basically one of our examples from section 6.1. We're going to add 1 to the exponent. So 3x squared will add 1 to the square, divided by the new exponent is 2 plus 1. And then from here, we're going to put our new line to show our limits of integration and put it from 1 to 4. Notice we don't put the plus c anymore. There is a reason for that. I'll quickly pull up this last page we just talked about. If you were to put that c there, you'd have f of b plus c minus f of a plus c, and it would be the exact same c value being subtracted. What would happen? The c's would cancel. So we don't need to worry about the plus c in these definite integrals as it goes away. It only goes away in definite integrals though. So simplifying this, we get 3x to the third over 3 from 1 to 4. The 3's will cancel because we're dividing, which leaves us with x cubed from 1 to 4. And now we can plug them in. We plug 4 in for x, we get 4 cubed minus, now we plug the bottom value in, 1 cubed, which when you evaluate that on your calculator would give you 64 minus 1, or 63. So the area under this curve is 63 square units, but we don't have to worry about the square units. It's a little counterintuitive. Normally we would always put that, but with these definite integrals, it's just always implied. And in some cases, with these definite integrals, it'll actually mean something besides area, which we'll talk about in the next video, where it can actually mean something more along the lines of income or a probability. Okay, so finally, not finally, sorry. So from here, that is, continuing on with this problem, I would like you all to pause the video and try to see if you can solve it on your own, and then we'll try it together in just a moment. So we have the integral from 1 to 4 of 7x minus 2x squared dx. Okay, so going through this together, to find the antiderivative of each term, we have the antiderivative of 7x is 7x to the 1 plus 1 over 1 plus 1 minus 2x squared. Again, we're going to add 1 to the exponent and divide by the new exponent. And all of this will be from 1 to 4. So we're going to simplify first. That gives us 7x squared over 2 minus 2x to the third over 3 from 1 to 4. And remember, once you've plugged in your once you've taken your antiderivative, you now plug them in and subtract. So we start with the top value always. We get 7 times 4 squared over 2 minus 2 times 4 cubed over 3. And this is all going to be minus, so once we plug in the top value, we now subtract when we plug in the bottom value of 1. So we get 7 times 1 squared over 2 minus 2 times 1 cubed over 3. And when you plug all of this into your calculator, you would be left with 21 over 2. So the integral from 1 to 4 of 7x minus 2x squared dx is equal to 21 over 2. All right, now for this last one, before we move on to our next fact, we have the integral from 5 to 5 of 10 minus 7x plus 128x to the 7th power dx. Now hopefully you caught this right away, but notice we are integrating from 5 to 5. Think about what our rule says when we're integrating with the same limit of integration on the top and bottom. The result will always be 0. The area under the curve when you have the same x value is the same thing as if you were multiplying a rectangle with a width of 0. The result is always 0. There's no work to show, it's automatic. Alright, so continuing on from there, we have a fact that says, when performing U substitution with definite integrals, you plug the interval values, meaning the limits of integration, into U's equation to find the new limits of integration. And then changing back to x's is now unnecessary. So when you substitute your limits of integration into your U equation that you found, you no longer need to change the integral's answer back to x values. It's automatically done for you. So let's show what that means. We have the integral from -4 to 1 of the square root of 5 minus t dt. So notice the complicated function in this is that square root. So we're going to let u equal what's inside of the square root, which is 5 minus t. And when we do that, that means du is the derivative of 5 minus t. So the derivative of 5 is just 0. The derivative of minus t is negative 1. And that's times dt. So remember, we always put a dx or dt if we started with dt at the end of our du. So plugging these values in, notice we do have our u value, but we don't have a dt, meaning we don't have a negative dt, that is, we only have dt. So to get that negative, we need to multiply the inside of our integral by a negative, which will give us negative dt for du, but doing so means we also have to multiply the outside by a negative. That's our rule we introduced before that said you multiply the inside by a constant and it's reciprocal to the outside. So we get the negative integral of negative dt is going to become du, and the square root of 5 minus t is going to become the square root of u. And finally, from here, we're not integrating from negative 4 to 1 anymore. Those were the t values. We're now integrating from, we're going to set up two equations here. u2, we're going to plug in 1 into our u equation to find its u value. So 1 will be plugged in here, which gives us 5 minus t is 1, which is 4. And then we'll plug in negative 4. We get 5 minus negative 4 for t, which gives us 9. And notice from here, we can't take the integral of square root of u. So just like when we dealt with derivatives in the past, to take this integral, we are going to have to change it to an exponent. We get the negative integral from 9 to 4 of u to the 1/2 du. Remember, whatever index value you have here becomes the denominator of your exponent. So if this were a cube root, we'd have 1/3. If it's a fourth root, 1/4, and so on. And now to find our antiderivative, we're going to add one more step before we start solving. We have a negative on the outside of the integral, and remember our rules say we can swap the limits of integration to get rid of that negative. So we get the integral from 4 to 9 without that negative of u to the 1/2 du. And now we can take the antiderivative. This is just one of our basic power rules. We're going to take u to the 1/2. We'll add 1 to the exponent and divide by the new exponent, 1/2 plus 1. And we're integrating from 4 to 9, which gives us u to the 3/2 over 3/2 from 4 to 9. Just a little bit of work left from here. We're just going to simplify, plug in our limits, and then solve. Whenever you're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So if you're dividing by 3 over 2, it's the same thing as multiplying by 2 over 3. So we get 2 u to the 3/2 over 3. Again, I'll say that one more time. If you're dividing by 3 over 2, you can change it to multiplying by 2 over 3. And that works for any fraction when you're dividing. That's from 4 to 9. And now we can plug in the 9 and the 4. We get 2 times u is 9 to the 3 halves over 3 minus, now we plug in 4, 2 times 4 to the 3 halves over 3. And when we plug this into our calculator, we're left with 38 over 3. Note that we never had to change back to 5 minus t for our u value because we changed our limits of integration to u values when we plugged them in to the u equation. Alright, so with that, I'd like you all to try this next problem, and then we'll try it together. Okay, so going through this, we're going to start by finding u. Remember, whenever you have a fraction, u is most likely the denominator or something in it. So we're going to let u equal x squared plus 10, which means du is the derivative of x squared plus 10. We get the derivative of x squared is 2x. The derivative of plus 10 is 0. So we get 2x dx. We do not have 2x dx in the original problem. We only have x dx. So we have to multiply a 2 to the top of our fraction. And when we multiply it there, we have to multiply 1/2 to the outside. Okay, so now we do have 2x dx, that's our du, and we also have x squared plus 10, which we said was u. So substituting these in, we get 1/2 times the integral of du over u. And now we just have to change our limits of integration to u values instead of x values. So we plug in 0 into our u equation, which we can even do right here, gives us 0 squared plus 10. And then we plug in 5, we get 5 squared plus 10. So we have 1/2 times the integral of du over u from 10 to 35. When we integrate du over u, we have 1/2 times the integral of du over u is the natural log of u. But remember, we need the absolute values. And this is all from 10 to 35. So I'm going to rewrite this because it's a little bit messy. We have 1/2 natural log of the absolute value of u from 10 to 35. And we can now plug in 35 and then subtract when we plug in 10. So we get 1/2 the natural log of the absolute value of 35 minus 1/2 the natural log of the absolute value of 10. Remember, these absolute values are very important because if these numbers were negative, the absolute values would get rid of those negatives. Otherwise, it would end up giving you a does not exist or error or undefined when you plug it into your calculator. And at this point, we can plug it into our calculators because the original problem said to approximate the final answer. And when you plug it in, rounding to the nearest fourth decimal place, you should get 0.6264. And that is our final answer.